Now we will now we will go for the derivation of the discharge over a triangular notch. So in the figure which is shown over there, a triangular notch is shown where this water is flowing, and this is the top surface of the water flow. And in order to derive this thing, the involvement of the parameters are such that this H, which is capital H, this is the head of the water above the V notch. So we can write that capital H is the head of water above the V notch, and theta is the angle of the notch. So for the derivation, we are considering any random strip into this notch. So we are taking a strip which is A, C and B. This strip is at a height of a small h from the top surface of the fluid flow. So if we talk about this particular strip of ACB, so this ACB is having a width of DH. Now if we enlarge this figure, and we can just again redraw the this particular strip in order to figure out the dimension. So we are again redrawing this thing. So this is your A, this is your C, and this is O. So this complete angle was theta, so this angle is your theta by 2. However, the OC is an important thing. So if you look at this thing, that overall length of the notch is capital H, and the height above the point C up to the top level of the or you can say the top surface of the water is small h. So the OC is capital H minus H. So this height is capital H minus H. Now we are not aware how much is the value of AC. So let's say this AC is your X. So we can write this thing as tan theta by 2 is equal to X divided by H minus H. So X will be H minus H multiplied by tan theta by 2. So this X is the half length of this strip. So overall strip is our strip length is your AB. Strip length is your AB, and this AB is equal to 2 times of X. So total length of the strip is 2 times of H minus H multiplied by tan theta by 2. So this is the overall length of the strip. So if we say what is the area of this strip, and let's say this area is dA. So area of the strip under the consideration, that is your dA, and this can be written as 2H minus H tan theta by 2, this is the length of the strip, and multiplied by the width of the strip, that is your dH. Now so the theoretical velocity of the water through this particular strip is again under root 2 GH. So the theoretical velocity of water strip, that is your Vt. So Vt can be written as under root 2GH. H is the head above the strip. So discharge through this strip can be written as dq. And this discharge is your area of this strip and the theoretical velocity. So your area is your dA multiplied by the theoretical velocity is Vt. Now we will put what the values we got from the above equation. So that is dq. dq is equal to dA we have already got, that is 2 multiplied by h minus h multiplied by tan theta by 2, and then dh, that is the area, and then the Vt is under root 2gh. Now we will quickly rearrange this thing, and then in order to get the total discharge we have to integrate over the height of the notch. So now in order to get the total discharge, that is your q, and that is the if we integrate this equation, that is integration of dq, and this is integration over the length of 0 to h of the equation we just wrote it above, that is your 2 times of h minus h tan theta by 2 multiplied by 2gh dh. Now we are doing the integration in the terms of dh, in the terms of the dh. So we have to take the where the h is available. So h is available at this location as well as this particular location. So just rearranging this thing, we can write it that q is equal to tan theta by 2 is constant, we are taking it outside, this is 2 tan theta, and also under root 2g is also constant, and rest thing we can write like 0 to h multiplied by h raised to the power 1 by 2 minus h raised to the power 3 by 2, and then integration with respect to the dh. Now the integration of this particular term will look like 2 tan theta by 2 under root 2g, and then this is h, then this will become h raised to the power 3 by 2 divided by 3 by 2 minus h raised to the power 5 by 2 divided by 5 by 2, and our limits are 0 to h. So this q is equal to 2 tan theta by 2 under root 2g, and then this will become 2 by 3 h raised to the power 5 by 2 minus 2 by 5 h raised to the power 5 by 2. So after rearranging the above equation, this will look like q is equal to 8 by 15 tan theta by 2 multiplied by under root 2g h raised to the power 5 by 2. So the final equation we are getting is this one. Second thing is, this equation is again the theoretical discharge. So in order to get the actual discharge, we have to multiply the CD value. So we can write that Q actual is just the multiplication of CD multiplied by 8 by 15 tan theta by 2 under root 2g h raised to the power 5 by 2. So the important thing, if you note down from our previous derivation, that once we were discussing the derivation related to the rectangular notch, the q was the proportional to the 3 by 2 power of the head. However, in case of the triangular notch, this q is proportional to the 5 by 2 power of the head. Now, if in order to get the some simple equation, or that the what values we are using for the various theta by 2, we can simplify this equation. Now the equation of the triangular notch we just got above is that q actual, that look like 8 by 15 multiplied by CD tan theta by 2 multiplied by 2g h raised to the power 5 by 2. If we go for a right angle V notch, then see the value of theta will be equal to the 90 degree. So that's make the tan theta by 2, that is your tan 45 degree, that will be equal to 1. And if we take a value of CD roughly equal to 0.6, putting all this values, we can get the equation of discharge, actual discharge for a right angle V notch. This value will be 8 by 15 multiplied by 0.6 multiplied by 1 multiplied by under root 2g, and we are taking the g as a 9.81, and then again h by h raised to the power 5 by 2. So this equation will be, after simplification, will look like 1.417 h raised to the power 5 by 2. So this is a equation for actual discharge for a triangular V notch, sorry, right angle V notch. Now important thing is that this equation is only this value of 1.47 is also valid when we have considered the CD value of 0.6 and G value of 9.8. If we take the G value as a 10 or a different value of CD, the same equation for the right angle V notch will be somewhat different. So in my opinion, you need not to remember this particular formula. If you are just remembering the original formula of the Q actual, then for any kind of V notch, you can with the given value of CD, you can figure out the final value of Q actual. Now we'll solve a numerical problem to find out the discharge over a triangular notch of angle 60 degree when the head over the V notch is 0.5 meter, by assuming that CD value is equal to 0.62. So let's start the solution. So the first thing that is given to us is the angle of notch is 60 degree, head is given to us, that is 0.5 meter, and CD value is 0.62. So the expression which we use for the triangular notch is Q is equal to 8 by 15 CD multiplied by tan theta by 2 multiplied by under root 2 g, then h raised to the power 5 by 2. So let's quickly put all the values. So 8 by 15 multiplied by 0.62, then tan 60 by 2 is tan 30, and degrees, you remember this point, and then under root 2 multiplied by 9.81 multiplied by h is 0.5, and that is raised by power of 5 by 2. So if we calculate this problem, this answer is coming out to be Q is equal to 0.1494 meter per second. So that is our answer. Now let's take a problem which involves the discharge over the rectangular as well as the triangular weir in the same problem. So the problem says that water flows over a rectangular weir 2-meter wide at a depth of 300 mm, and afterwards passes through a triangular right angle weir So taking CD for the triangular and sorry, the taking CD value for the rectangular and triangular weir as 0.60 and 0.58 respectively, find the depth of the rectangular weir. So the problem is such that this problem is like water is flowing through a channel, and first it is passing through the rectangular and then it is passing through the triangular notch, and in both cases the same amount of water will be flowing. So the determination is such that whatever the q input is over there, that will be again the q output from the v notch. So what exactly we have to do, we have to find out the values, I mean the dimension of the rectangular weir, and based upon the dimension of rectangular weir we will determine the q value, and then we will equate the same thing that we obtained from the triangular notch. So let's start solving this particular problem. So for the solution, the values are given as L, that L is equal to is 2 meter wide, and height that is 300 mm, that is 0.3 meter, that is 0.3 meter, and CD value for the rectangular notch is given as 0.60, and we are using a triangular right angle weir, so theta is equal to, that is 90 degree, and for this triangular weir the CD value, it is 0.58. So these are the values for the rectangular one and this is for the triangular one. So what we are assuming that the discharge over the rectangular weir, that is known to us. So based upon this one we will figure out the value of q. So that is q by 3 CD multiplied by L multiplied by under root 2g multiplied by h raised to the power 3 by 2. So this is 2 by 3 and CD value is 0.60, L value is 2 multiplied by 2 multiplied by 9.81 multiplied by h is equal to 0.3 raised to the power 3 by 2. So this value of q, will get it as 0.5852 meter cube per second. So that is the discharge we have measured from the rectangular weir. The same discharge is passing over the triangular weir. So we will use the equation of the triangular weir, that is q is equal to 8 by 15 CD multiplied by tan theta by 2 multiplied by root 2g h raised to the power 5 by 2. So we are just going to put the all values, that is, so q value is 0.5852 is equal to 8 by 15. CD value is 0.58 multiplied by tan 45 degree, that is tan 90 by 2. So this value is V1 multiplied by 2 9.81 multiplied by h raised to the power 5 by 2. So this h value is unknown to us. So h raised to the power 5 by 2 is equal to 0.4271. So h is equal to 0.4271 raised to the power 2 by 5. So that is 0.711 meter. So that is our answer. If the discharge is first of all passing through the triangular weir and then passing out to the rectangular weir, we can take a similar problem. So let's go for the other problem that says that water flows through a triangular right angle weir first and then over a rectangular weir of 1.5 meter width. The discharge coefficient of triangular and rectangular weirs are 0.65 and 69 respectively. If the depth of water over the triangular weir is 0.4 meter, find the depth of water over the rectangular weir. So let's start the solution. So the solution for this problem, so first of all we will note down all the values that is given to us. What it says is that in here the rectangular weir h is 1.5 meter, and so the values given to us is for the rectangular weir L value is 1.5 meter, and CD value that is 0.69, and for the triangular case that theta value is given to us. So theta is 90 degree. So for the triangular one, theta is equal to 90 degree, and another thing is CD value for this one is given, which is the 0.65, and uh, H is given, that is 0.4 meter. And in this case, what will be the H value that we have to determine. So let's start the problem. So first of all, here the scenario is such that first of all a triangular weir is there, and the same discharge is passing through over it, and again it is going through a rectangular weir. So again the Q discharge will over there. So this is the quantity that we have to equate from the two different shape of the weirs. So figuring out this solution for this problem, that is Q is equal to 8 by 15 multiplied by CD tan theta by 2 multiplied by under root 2g h raised to the power 5 by 2. So it is 8 by 15 multiplied by CD is 0.65, tan theta by 2 is 45 degree, I mean 90 by 2 is 45, tan 45 is 1, and then under root 2g 9.81, and then h is given to us, that is 0.4 raised to the power 5 by 2. So this Q value is coming out to be 0.1554 meter cube per second. Now this is the same discharge which we were talking about. Now for the rectangular case, this discharge value is given to us. So Q is equal to 2 by 3 CD multiplied by L multiplied by under root 2 G multiplied by H raised to the power 3 by 2. So Q value is 0.1554 is equal to 2 by 3, and CD is 0.69, L value is 1.5 meter multiplied by 2 into 9.81, and then h raised to the power 3 by 2. So h raised to the power 3 by 2 will be equal to 0.0508. So h is equal to 0.0508 raised to the power 2 by 3, that is coming out to be 0.137 meter. So the answer for our problem is h is equal to 0.137 meters. So let's take a very interesting problem where a rectangular channel which is 2 meter wide has a discharge of 2500 liters per second, which is measured by a right angle V notch Weir. Find the position of the apex of notch from the bed of the channel if maximum depth of water is not exceeded by 2.5 meters. We have to take the CD value as 0.6 meter. So if we draw the sketch of the particular problem, where the channel which is shown is over here is a rectangular channel, in which a V-shaped or you can say triangular notch is established, and this notch is such that it is at the some height above the channel bed. So this is the channel bed, and let's say the value this is x, and above the x above the apex water is flowing, and let's say this height above the crest of the weir is h. So in the particular problem, the maximum depth of is not should be set between the 2.5 meter, which says that. So we are starting the solution. So the statement which is written over there, it says that h plus x should be 2.5. If we figure out this particular thing, then everything is possible to resolve. However, the q value is given to us, and where we can relate the q value with the h. Once corresponding to q, you can get what h should be there, and then you just add the subtract the h value from the 2.5 meter. You will be able to figure out the x that is the required from this particular question. So let's start with this one. So the channel width is given us rectangular channel width b is equal to 2 meter. So this channel is 2 meter wide, which is not required in the any place during the solution of this problem. So the rectangular channel is 2 meter wide. The next thing it says that it has a discharge of 2500 liters. So Q is equal to 25 liters per second. That means 2.5 meter cube per second. Find the position. So it is a right angle notch. So theta is equal to 90 degree. And CD value that is also given to us is 0.60. So we will figure out the discharge over the triangular notch, that is Q is equal to 8 by 15 multiplied by CD multiplied by under root 2G multiplied by tan theta by 2 multiplied by h raised to the power 5 by 2. So Q is 2.5 is equal to 8 by 15. CD is 0.6 multiplied by 2 into 9.81, and tan theta 2 by 2 will become to be equal to 1 because this theta is equal to 90 degree, and then h raised to the power 5 by 2. Another important thing that this particular value you will require many a times once you are solving the Weir notch, and this value usually comes out to be 4.429. So for your ease, you can have you can remember this value. So every time you need not to take the root of the 2 into multiplied by the 9.81. So the h raised to the power 5 by 2 will be equal to, that comes out to be 1.7637. So this value will give the h value is equal to, this value is coming out to be 1.2548 meters. So h is known to us. Now the value of the h plus x is given to us, that should be 2.5. So let's say this is equation 1, and this is the equation 2. So let's solving the problem from equation 1 and 2. So this is 1.25 plus, we can write the exact value, 1.2548 plus x, that should be 2.5. So x is 2.5 minus 1.2548, that is coming out to be 1.245 meter. This is the our answer, that this is the position of the apex of the notch from the bed of the channel.